All right. So today what we're going to spend our time doing is talking about power and confidence intervals on effect sizes. There's some stuff that happens when we start to try and calculate confidence intervals on effect sizes that gets a little bit tricky. So we're going to go through and spend some time talking about that. In general, kind of our map here, going to start with conceptualizations of power and think about what power is, what it means, a couple different ways we might think about it, talk about factors that influence our power, introduce you to non-centrality parameters. These are kind of like raw metrics of effect size, but they start to become important for conceptual reasons. Going to calculate power, talk about problems with observed power. This is a thing that SPSS provides that's not terribly useful for much of anything, but people will get hung up on it sometimes. Talk about problems with confidence intervals on effect size, some non-centrality parameters. It was kind of advanced at one point. It's less now that sort of we've got stuff to go through and do it, but we'll talk about that. And then finish up with calculating our confidence intervals around our measures of effect, or our means-based measures of effect. Okay. So we go back through and talk about our experimental error. Okay, we've got two types of experimental error. What are my two? Someone help me with my two types. What happens with a type 1 error? Pasha, go for it. I reject the null when it's actually true, right? So I say, I'm going to say that I have evidence for an effect when in fact there is no association in the population. There is no difference in means across population. I've claimed to have something that I don't, right? Thinking about type 1 is kind of getting away with something, right? I've sold you a bill of goods. I say, hey, this is a product that works when in fact it doesn't. What about type 2 error? Yeah. I failed to reject a null that's actually false. So I say, hey, inconclusive, right? I'm not saying that the null is true. I'm just saying I don't have evidence to say that the null hypothesis is false, when in fact, in real life, the null actually is not false, or the null is false. There is a difference. There is an association, so on and so forth. Okay. With our analyses, we're generally concerned with controlling our type 1 error. What controls? I got a mustache hair in my nose. That's uncomfortable. What is, how do we go through and control our type 1 error in our tests? What controls that? Do you know?
Wouldn't like using measurement?
Okay, so yeah, so method stuff will improve our overall error. But what do I set in my statistical test to set my type 1 error? My alpha, right? And so I set it at 0.5. I'm saying I'm willing to be wrong and make type 1 errors about 5% of the time, right? And so it's a big thing. We actually don't set them, like the industry sets them. If we were trying to screw around with that, we'd probably have to give a reasonable justification for why we were doing that. Theoretically, there are reasons we might, but that's generally kind of what we've got going on, right? Typically we're typically end up being less concerned with the possibility of type 2 errors, although this is changing. But why historically might it be problematic that we're ignoring type 2 error? Particularly given the way we've run our science for the past 100 years. Yeah, Emily.
Suggesting about how we expect there to be a difference, so that it fails to reject that
Yeah, a lot of it has to be with how we typically interpret, like even, and I'm guilty of this all the time too, right? Say, oh, a null effect, so like, okay, nothing to see here. It doesn't mean nothing to see here. It just means we don't have enough evidence to say there is something, right? But what we often do is we interpret null a fail to reject as meaning zero difference or zero association. And from a mathematical standpoint, from a Meal standpoint or a Cohen standpoint, is that ever the case? No, we always say that the null is always quasi-false to some extent, right? And so when we're not paying attention and we're not concerned with type 2 errors, what we start doing is we start evaluating things and say, oh, we don't have evidence for this. When, as in some of the examples that you're working through in class, there may be good reason for why we aren't able to, and predictable reasons why we're not able to identify differences, right? And so what do we make more often? Type 1 errors or type 2 errors? What do you think, Katie? Type 1, which one do we make more often? Okay, so there we go. We sort of default. Yeah, why do we make, because type 2 errors, like if our alpha is saying we're only going to make the nature of our test said we're only going to make type 1 errors 0.5% of the time. How often do we have adequately powered studies in psychology? Half the time at best, maybe, right? And so type 2 is the error that we're probably making far more consistently across a lot of our research, okay? And our concern with type 1 errors, again, so the reason we're talking about this and why you probably maybe mentioned type 2 errors in your intro stat class, but didn't focus on it further, is they're not relevant to how we've structured our null hypothesis test. Null hypothesis test is all around type 1 error, right? And trying to avoid type 1 errors. Historically, it's been really hard to get a precise calculation of type 2 error. It's mathematically kind of difficult. Now we have the wonder of computers. It makes it much easier to go through and do this directly, but there's still, and we'll talk about this later, power analyses are much more like throwing horseshoes than target shooting. We're just kind of getting an about type of thing for reasons we'll talk about. Other thing, awareness of type 2 error is inconvenient, right? If I go through and I put together, say Teresa puts together a thesis, and she says, this is what I want to do, right? Type 2 error makes me sad because if I don't have enough people, if I don't have a good enough manipulation, if I don't have access to the populations that I need to be doing, the likelihood of my type 2 error goes up and up and up, and then it starts to become uncomfortable, right? You can think about type 2 as an investment. Power analysis is an investment. If I'm going to invest time, effort, whatever, into this project, what's the likelihood of me actually coming up with an effect that's there, right? And the answer is often not good, right? And so this is why over the past maybe decade or so, sort of even more recently, there's been a much heavier emphasis on power analyses, particularly among you experimental folks, saying, hey, this is what you're going to do. I want to see evidence that you have enough people in this study to be able to detect the effect that you think is going to be there, right? Because otherwise, particularly for grant-related stuff, why would I give you a bunch of money to run a study that has maybe a 50% chance of detecting this effect that's actually there? It doesn't seem a good return on my investment, okay? So this is why, and it's one, it's kind of tricky, it's hard, it's sort of kind of heady, and then also it often doesn't give us the types of analyses that I want, right? So this is someone, regularly students will come back, oh, I need to figure out how many people I need for my moderation analyses. That's cool, I can do that like that in my head. The answer is more people than you're probably going to get. So just say, I'm going to get as many people as I can, and we'll run from there, okay? All right, so if we're talking about power, thinking about power, we note this is 1 minus beta, okay? Talk about this as the long-term probability of rejecting the null given a particular effect size, alpha, and sample size. Again, this sort of pulls into the frequentist approach if we're talking about an infinite number of replications. Never in a manuscript say an infinite number of replications because people get aggravated with that. But theoretically, this is what we're talking about. If we were to do this over and over and over and over and over again, how often are we going to reject the null hypothesis given a particular effect that we're hunting down an alpha and an n, okay? These power analyses need to be, if we're doing this right, we're trying to determine the expected power of a study before we collect data. Before I even go out there, how many people do I need to power this study in order to have a reasonable chance of detecting this effect that I think should be out there? Okay. Again, either determining the sample, or maybe we're saying this is how many people I can get, which is more often kind of the situation, right? Because we rarely have access to infinite resources. Just go through and get all the people. So I can say I've got 2 semesters to collect this data. I can probably get this many people. What's the power of this study going to be if I were to go through and do that? Okay. But again, this is all before we go through and collect data. Okay. Now, the problem is this is not an exact science. As I said, it's more horseshoes than anything else, or hand grenades, if you prefer. In general, we're trying to get a better sense. Are we closer to 0.8 or 0.3, right? Like, am I likely to reject the null on 80% of these replications or 30% of the replications? Okay. Why might this be? If what goes into my power analysis, I need to know an effect size, an alpha, and a sample size. What's the real tricky piece of identifying in those components? Alpha is easy. That's kind of set. Sample size, it's just a number. That power, that effect size. So why might it be difficult to know what effect size I'm trying to chase down? What do you think, Sam?
A priori,
What's that now?
like a priori.
A priori, yeah, a priori. Why might it be difficult to know what effect size I'm looking for? There could be discrepancy in the literature, right? Okay. Yep, also a good point. Might have bias there, right? Okay, so maybe I've got a lot of studies out there, and different studies are reporting different measures of, or different estimates of effect. They're also using different populations and different methods and different measures. Know that probably our reported effect sizes in the literature are probably biased, just the way our have a positive bias, just because of the way things work. So all of a sudden that starts to complicate things a great deal. Meta-analyses help a little bit, right? If we can get a nice a nice metric or aggregate measure of effect, that can be super helpful, right? And even with that, if it's a good meta-analysis, it's probably got a lower bound or upper bound for effect. So that gives us even more of a sense. So that's good. But even with all that, what complicates this? I'm doing cool research that is unique and interesting. Yeah, maybe no one's ever done this before. No one's asked this specific question. A lot of the times, this is what happens. Like, I'm interested in the extent to which, just like give me an X and a Y, sort of a predictor and an outcome that you're interested in.
Interested in prior how political somebody is, like how likely they are to change very quickly.
Okay, so we've got like political, let's call it sort of political orientation and sort of susceptible to sort of change arguments or something like that, right? And so maybe that's what I want to look at, but then I want to see the extent to which SES changes that, right? Maybe no one's ever looked at that before. It might be a reasonable question, but there's no data. No one's actually run that to see what that specific effect is. And in that case, I don't have anything to go on, right? It makes it very difficult to go through and start to go through and do this because, one, I need to have a good estimate of the effect that I'm hunting down. That's always the key. What's the effect that I'm trying to chase down? And then I can work backwards from there, but that's often very difficult for all the reasons that we've talked about, okay? So what we do is we end up playing a lot of guesswork, okay? Now, with when we're talking in psychology about an adequately powered study, right? We're always saying, sort of our reference point is 0.8, okay? But again, this is a kind of a rough estimate, okay? the argument being that if I've got power less than 0.8, this is unacceptable type 2 risk. I'm saying that less than 80% of the time am I going to find this effect that's actually out there in the universe, right? And so we might say, well, you need to have higher, but recognizing that we can also have power that's too high, right? We can have too much power. Too much power is going to corrupt us, maybe, right? Because we can say, if I got a sweet repeated measures design, right? And I only need, say, 40 folks to detect this effect that I'm looking for, and I go through and run 100, I didn't need to do that. It's way too much. Like, I don't have anything. I didn't need that many people. It's not a good use of resources. And also what might end up happening, again, as we talked about the impact of effect size on rejecting the null, and sort of the idea, at least in theory, the null is always false. Like, if I just get enough people in my sample, I'm always going to reject the null, right? What we can start to do is start to make unwarranted conclusions. Say, again, review the paper where they're making a big deal about finding some sort of, the two groups were different in a sample of over 100,000. I'm like, sure. I would be shocked if you didn't find that there was some trivial difference, right? We've overpowered something. And if we're not being careful, we can start to sort of make conclusions about, like, things are a big deal when in fact they're not. Okay. So if we're thinking about how we go through and think about power from a conceptual standpoint. So a couple different ways we're going to do this, but let's say, and an example, I know, experimental folks, I don't know if you, stereotype threat, is stereotype threat still a thing, or did we debunk stereotype threat? Is it still a thing? Okay. Sometimes I don't know if all my examples are relevant, but here, what we're doing is we're looking at stereotype threat. For those of you who don't know or might not be familiar, this idea that if I'm primed with a stereotype that's relevant to my group, that can inadvertently start to impact sort of my performance, right? And so what we've got here is a study where what we did is we took white men. We're going to give them a math task, but before we give them that math task, we have a control group where we just let them take the math task, and then we got a threat group. We say, oh, hey, here you go, finish this up. Oh, P.S. Asian students do a lot better on these tests than white people do. Okay, it's probably more explicit than sort of the actual manipulation they had, but sort of you get the sense. So we've got a threat group, and then we've got a control group. Okay, and what we found here, let's say that for our control group, 20 people in our threat group, mean of the control group performance 9.64, mean of our threat group lower at 6.58, and then we've got our standard deviations. Okay, so let's say this is one study. Okay, but let's say that this, and so this is the only study that we have to base on, right? Elizabeth is going to do her thesis on this, and so this is the study that she's basing her power analysis on. Okay, so absent any other information, these are the best estimates that Elizabeth has on the true population estimates. Elizabeth, do you think the control group really scores in the population? We took all white males and put them together and had them take this math test, that the exact mean would be 9.64.
I don't think that is fairly representative of the general population.
Okay.
Only looked at males. Right?
Yeah, and so that's technically the population of focus here. So that is, but probably our point estimate of our sample is probably not going to be exactly dead on, right?
Oh, yeah.
Yeah. Same thing with the threat. Is it going to be exactly 6.58? But it's the best that we have because it's the data that we go on, right? So if we were to go through and we were to create a population of scores, right? And with the power of computing, we can do this. Right? If I said in the bowels of a computer, generating a normal distribution with mean equal to 9.64, standard deviation equals 3.17, okay? And I were to go through and randomly select 20 observations from this distribution of scores, okay? And then I'm going to go through and do the same thing, but this time I'm going to create a different empirical distribution, population of score. This time I've got mean equals 6.58. Standard deviation is 3.03, okay? And I were to go through with, this is my thread, right? In big capital letters so that you know it's for real. Otherwise, you do not think it's threat. Go through, pull 20 scores from this, okay? And so then what I do is then I calculate and the test statistic. So I take the mean of the 20 people I pulled from this. And the mean I pulled from this. And whatever those two means are, and whatever those two deviations are that I pulled from these two populations, I go through and I record a test statistic for that. Okay, people see what I did? So this is a billion scores, this is a billion scores. I pulled 20 from this, 20 from this, ran a t-test with that, okay? Then I'm just gonna do it, say 1,000, 10,000 more times, okay? If I were to do this over and over and over and over again, and I were to plot out these test statistics across these 10,000 replications, pulling from this population and this population, and I plot this out, what have I created here? Emily? A frequency is what? Yeah, a sampling. I've got a sampling distribution of t-scores, right? So if from the Aronson study, if we're presenting that that's straight on, right? And so I've got a population with a mean of 9.64 and a population with a mean of 6.58. I know that's not true, but it's my best stand-in. I create a distribution of scores here, sample 20 times from each, and then I just calculate my t-statistic and then just do this 10,000 different times. What I'm going to get is I'm going to get a sampling distribution of t-scores, right? And then what I'm going to do is if I'm going to go through, I'm going to look at this, and I know that for a independent sample test with 20 in each group, my degrees of freedom is 38, and my critical value for a t-statistic with 38 degrees of freedom is 2.04. I go through and mark that on this distribution. My mean is just 3.12 because that's, if I go through, right? I say the first group is 9.64. Oh, what are you doing? .64, 6.58, standard deviation 3.17, 3.03, sample size 20, 20. Here's my t-statistic, right? My test statistic is 3.12, and my p-value is 0.003 on that test. So that's what Aronson and colleagues got. And if I were to go through, and if I'm using those as the reference point for my two across my replications, my sampling distribution is going to be equal to my population t, which is 3.12. Well, what I can do then is on this distribution, I can go through and say, okay, my critical value is 2.024. I can mark this, and then I can say how many t values or what percentage of this distribution falls at or above sort of my critical value, right? Because any of these tests across these 10,000 replications, any of those tests, that I get a t value of 2.024. Amanda, what do I do in those replications? Do I reject or fail to reject? Yep, if they're that. Okay, so we're not really looking at critical regions here. This is just like sort of the proportion of the distribution here, right? So if my critical value for a test with 38 degrees of freedom is 2.042, if I, across any of these 10,000 replications, if I get a test statistic of 2.042 or greater, what do I do? I reject or fail to reject? Yeah, I reject the null. These are, of those 10,000 replications, any of those with a t-statistic of 2.042 or greater, those are the ones I get to reject, right? And my t-statistics go all the way like sort of super high, right? There's a whole range of stuff that I can get, right? But Baja, what happens in those tests, in those replications where I get a test statistic less than 2.024? What do I do there? I fail to reject, okay? And I see here that I've got some portion that I'm going to fail to reject, right? What does this white area represent? What are those? Those are type 2 errors, right? These are situations. So even though I know that my threat group is different than my control group, I know that, right? Because this is my population, right? But on some portion of these replications, I'm going to fail to detect that difference. My test statistic is going to fall below that critical value. And so in those replications, I'm going to fail to reject. I'm going to make a type 2 error. Even though in the population there is an effect, what I've gone through, and on some portion of these 10,000 replications, not all of them are going to find that effect. This is my type 2 error, and this is my power. So whatever this area is in this example, so the area under the curve here is 0.86, right? So I would say in this example, my power is 0.86. 86% of the time, if I'm pulling samples of 20 from each one of these two populations, 86% of the time, I'm going to reject the null hypotheses. This is the long-term probability of rejecting the null hypotheses given an effect size, a sample, and an alpha level, right? So they're 15% of the time, 14% of the time, I've made a type 2 error, right? People kind of see sort of empirically what power is looking like from this perspective. Yeah.
Kind of curious what you mean by long-term probability, specifically the long-term part.
Long-term, over sort of replication. Okay, so Matt, if I happen to be down here, right? So this is over 10,000 replications. It's probably, you're not probably over the course of your lifetime ever going to spend 10,000 replications of the same study, right? But if Katie, you're just doing one study, right? And you fail to reject because you're down here, do you know where you are in that distribution? You don't know where you are. All you know is you're right here, right? So it starts to make it very difficult. But long-term, think about this as a Vegas bet, right? Like if I'm there, if I've got, if I know I'm going to win 86% of the time, I'm going to show up at that game with a whole bunch of money, and I'm just going to play and play and play and play and play. Okay. What if my odds of winning are more closer to what they are in gambling? And let's say it's 0.46. Am I super excited about that? Right, no. Does that mean I'm not going to find something? Nope. But I'm not going to find stuff more often than I am going to find stuff. And so then I'm just kind of rolling my dice. Essentially what I'm doing if I've got an underpowered study is I'm just going to roll the dice and hope that I overestimate my effect size in this given sample and get on the higher end of stuff. It's kind of a garbage thing to hope, but that's essentially what we're doing anytime we go through and we run an underpowered study. Questions about this? People kind of wrapping your head around kind of seeing how this is working? Okay, so this is a nice empirical demonstration. Oh, whoops, I ran over. Let's go through, take a break. Let's come back at 10 till, and we'll jump into kind of the next thing. All right. Feeling comfortable with this stuff? All right, cool. So here I'm going to give you a different way to think about this. Okay. We can also think about power as the result of overlapping distributions. And this is probably the more sort of probably helpful conceptual way to be thinking about some of this stuff, okay? So what we're working with here is sampling distribution of the mean when the null is true, okay? And this is what we're typically working with in a situation where with our null hypothesis, okay? So we've got a sampling distribution of our test statistic. And this is the distribution when the null hypothesis is true. This is just your t distribution. This is the distribution we're using all the time. This is the one we know and love and working through here, okay? We've also got the distribution of the mean when our null hypothesis is false, okay? When our null hypothesis doesn't map onto our alternate hypotheses, or excuse me, when our data aren't, when the null is false, when sort of we've got a situation, which is what we hope, right? That the null hypothesis isn't true, that our groups are different, that there is an association, so far and so on and so forth. If we're working with a situation where the mean isn't zero, or the difference isn't zero, or the relation isn't zero, now we've got all of a sudden what happens is we got a new distribution layered on there. Okay, so this is my distribution under the null. This is what I'm assuming the null hypothesis is true. This is what should happen. But in actual fact, if things are going our way, we don't have that. We've got a null, an alternate distribution when this is false. Okay. Now, if we are running this distribution under the null, at some point here, right, we have our alpha level, right? And so this is whatever our critical value is, alpha 0.05, right? And we've got this p here. And under my null hypotheses, Amanda, what do I do if I get a test statistic that's here in this table?
That's critical.
That's my critical. Yeah. So what do?
If it falls in the critical, reject.
I reject the null. Okay. So assuming that the null hypothesis is true, this is the distribution of my test statistics. And if I find a stat out here, I would reject the null and saying that if the null hypothesis is true, if the null hypothesis is true, this is where I'm making my type 1 error, right? But in actual fact, if the null is not true in the population, this isn't the distribution I'm working with. This is the distribution I'm working with, right? There actually is a difference. And the offset and the placement of this distribution is dependent on my alternative hypotheses, how much of a difference that I have in here. So if under my null, assuming that the null hypothesis is true, I land in here, and what I do, I reject the null. And if the null hypothesis is true, I've made a type 1 error, okay? But if I've gone through and the null hypothesis isn't true, right? That there actually is a difference, I'm working with a different distribution. I'm working with this distribution right here. What happens if I land anything in my actual distribution that's actually in real life? All this stuff, what's going on here? What decision if I find test statistics in over here? What am I doing here? Am I rejecting or am I fail to rejecting? I'm rejecting, right? Because I'm getting test statistics that are larger than my critical value, right? And I would hope that those test statistics, if the null hypothesis is true, I'm hoping that that's happening less than 5% of the time. It's actually happening a bunch of times, okay? But what happens if this is the distribution I'm working with, the green distribution here, what happens if I get down on this left tail? Yeah, right? So I'm failing to reject. What's happening if I'm over here on this distribution? What type of error am I making? The type 2 error, right? So what I've got is actually, we can think about power as overlapping distributions. We got our null distribution. This is the distribution that we're testing on, right? But we've got actually what's going on, the distribution out there in the real world, which is what we're hoping is a distribution of scores given the fact that I'm assuming that nothing's going on here, right? And so in this situation, here's my critical value based on my null distribution. If I get a test statistic that exceeds that, I'm going to reject the null hypothesis, right? And the null hypothesis is not true, then I've made a correct decision, right? But even with that, even if the null hypothesis is true, there's still part of this distribution that's overlapping with my null distribution. And if I land in here, this is where I'm making my type 2 error. I failed to reject the null hypothesis, even when the null hypothesis is true. Okay. And so again, if we go through and we take a look at your slide here, this is my critical value, right? Under my null distribution. And so if I get a t statistic that's anywhere from here over, that falls in that critical distribution, I get to reject the null hypotheses. If this is the actual distribution I'm working with, right? Not the alternative, anything over here, this is all power. Here, though, here are my type 2 errors, okay? So different than what I've got in my example here, what's the power look like in this set of overlapping distributions, Teresa?
It's a lot less overlap. Wait, no.
There's more overlap. And which one of these do I have more power? This one or that one? So thinking about remembering that power is my ability to reject the null when the null is false. Okay. So do I have more power in this figure or that figure? That one, right? This one, there's more overlap, right? There's more potential for me to, even if because this is the distribution in real life, H1 is what I'm working on. These are the things that I'm dealing with. But there's a lot of H1 that overlaps with my null distribution. And if I get anything in there, even if I dead center get on the right, even if my test statistic is consistent with the population value, I'm still overlapping in the null distribution. I'm still going to fail to reject, even though I'm dead center spot on with my estimate, because I don't have a very good power. In this situation, different. There's less of an overlap. I've got a more power there, a better powered test there. Yeah.
There's more overlap and there's more potential for type 2 errors.
Yeah.
Okay.
Yeah. Yeah. So, and again, if we go through and we switch this around, right? If I go through and I increase the difference between the null and the sort of my population value and my null value, as that distance increases, those distributions become less and less overlapped, which does what to my power, Elizabeth? Yeah, as the difference between my null value and my actual population value in these distributions starts to increase, what does that do to my power? It increases my power, because here, relative to here, what might I infer about the effect size here versus here, all things considered? Or do I have a bigger effect size? The bottom one, right? I've got more of an effect to test. So all things being held similar, I've got more of effect, less overlap here. And so even though there are portions of my alternate distribution that are overlapping with the null, more of it is not. And so these are the replications that I'm going to go through and test. These are going to be my type 2 errors. Yeah, Josiah.
This is probably just for me. I'm just trying to conceptualize it.
Yeah.
Those are the same study. The top one has less distance to the bottom one.
Yep.
The bottom one has more power. Would it kind of be like, instead of them like moving apart, would it kind of be like they're getting smaller?
Yep.
Okay.
Exactly right. So the question is if I have more people, I would expect the variability of these distributions to shrink up, right? My standard error is going to get smaller. And so that's why if we're saying all things being equal outside of the effect size, right? So in this case, let's say I've got 20 people per sample, 20 people per sample. So the distribution is going to be the same. It's just here I'm looking at a smaller effect than this. Now, if I were to go through and have take this distribution or this situation with sort of whatever effect size this is and jack up the number of people that I have, those distributions would shrink up, causing them to overlap less, but the distance between the two means is going to be the same, right? So there's a couple different ways that can go. Yeah.
If they shrink, because like the more people you have, it's supposed to be.
Yeah, I have less variability in that sampling distribution, right? And this is, and what do I call the variability in my sampling distribution? What is it?
Standard
It is standard error, right? My standard error is going to get smaller, right? So those test statistics are going to vary less from point to point. I mean, there's still going to be some at the tail, but this is what happens, right? You know, if I'm thinking about power, thinking about effect size and sample size, right? Either one of those things can go through. Now, sometimes I can't do anything to change my effect size. Sometimes I can, but oftentimes I can't. The effect size is the effect size, but what I can do is increase my power, reduces the standard error, and that overlap starts to decrease. Okay. So, and this difference between the null value and the actual population value that we're looking at, this is going to be our non-centrality parameter. This is sort of a metric of effect that we need to go through and determine. Okay. So influences on power, we've got our effect size. The magnitude of the difference between my null value and my actual population value. As my effect size that I'm chasing gets larger and larger and larger, the more power I have. Okay. My alpha level, as I increase my alpha level, that increase power, right? So if I go, say I'm running my tests at 0.1 as opposed to 0.05, I'm going to more likely to reject the null, but we often can't fool around with that because we'll get in trouble with reviewers. So, but we could influence power by changing that. Population variance, okay? Variability in the distribution of sample means as that increase, that's going to increase as my population variance increases. So if I'm looking at something that in a means-based test varies widely across within my group, that's going to increase my population variability estimate, which is going to increase in theory my sampling estimate, which is going to increase my standard error, and so my power is going to go down. But there's not often much we can do. Variability of sampling distribution is called what? Standard error, right? So as my standard error increases, my power decreases, and then my sample size, right? Variability of my sampling distribution decreases as my sample size increases. Again, anytime we're talking about variability of my sampling distribution, we're talking about standard error. I jack up my N, standard error goes down, and I get much more powerful tests with that. Okay, so here, almost always our efforts to increase our power are typically going to involve increasing our sample size. Okay. Because there's often not, we can't screw around with alpha. Generally, there's not much we can do with population variance, although we can if we start to get better estimates and better measurements. The variability to just due to random garbage is going to decrease. So our methods can help there to some extent. Effect sizes, that's often just what it is in the population. We can start to go through and do things, use extreme group designs. So I'm looking at, for let's say clinical folks, I'm comparing people with alcohol use disorder against people who have never had a symptom of anxiety, depression in their entire life, right? That's going to increase the effect size. What you might end up with is groups that aren't a comparison group that's not reasonable or representative much of anybody. Experimental folks, if I go through and I increase the power of my manipulation to something that's quite small versus something that really smacks people over the head, that's going to impact my effect size, right? So there are design related things where we can do things to change this, but in general, sample size is generally what we're looking at to increase the power of our tests. All right, so estimating our effect sizes. What we need to do before we run a power analysis, we need to have some idea of what effect we're hunting down. First thing we should always be looking at is existing research, okay? And also why it's important to report means and standard deviations in our reports, right? So that even if we don't know what our research will be used for at some point in time, someone may be interested in looking at variables that I included in my study that I wasn't necessarily interested in. But if I report means and standard deviations, they can go through, calculate effect sizes on their own, and then use that to help run their power analyses, right? So Basha wasn't looking at X and Y in hers, but I'm interested in doing this. She happened to include in her study. She was kind enough to report means and standard deviations and test statistics. I can go through and generate an effect size off of that, right? But sometimes there's no one who's done stuff that's looked at sort of what we're doing, right? Sometimes there's just not anything out there. In this situation, what we could do is we could step back and say, how large of an effect do I need, right? And in some type of applied situations, I could say, how much of an effect would I need in order for this to be meaningful, okay? Sometimes this is hard. A lot of the stuff that we're looking at in our research is theory-based. I'm looking at evidence for sort of some conceptual model or not. In that, it's hard to say how much is important, right? A lot of the effects we're chasing down is small. But in applied settings, when you think about clinical folks, right? We know we've got sort of X, Y, and Z treatment modalities out there. I want to put together another one. If this thing doesn't create a magnitude improvement that at least is as good as the other stuff, then maybe it's not worth even checking out. So what I can do, I don't know, this is a new treatment that I've developed. Who knows what the effect is going to be? And so who knows how many people I need to adequately power this? What I might say is this is what's out there already. If my study doesn't detect an effect of at least this size, then who cares if it's working, it's not zero, but it's just a smaller effect than that, then I would say, all right, I need to see an effect size of about D equals 0.4. I need to see at least a 4/10 of a standard deviation reduction in sort of whatever I'm seeing in order for this to be worthwhile. So who knows what the effect is going to be, but I'm going to power this study to at least be powered to detect an effect of 0.4. And so then if it turns up null, then who knows, but I at least, maybe it's got a lower effect, but I at least powered it so that it would detect effect that I would need. Kind of clear on what we're doing here? All right. Last thing we can do is we can use conventional cut points, right? Say, if we've got no idea about what a practical effect would look like, and no one actually has ever done this before, what we can do is step back and we can say, well, I'm looking for a small effect, or I expect a medium effect or a large effect. But what I will say is if we're down to this stage of the game, there's really probably no credible reason for you to expect a large effect or a medium effect or anything other than a small effect, given that in psychology, we're almost always looking at small effects, right? If you just say, oh, I'm powering this because I expect a large effect, and that's it, your hopes and dreams and wishes aren't a real compelling reason to expect a large effect size. Probably you're just saying I expect a large effect because that gives me a more manageable sample to be collecting. And this is where that issue came in with asking about, oh, what do I need to power my moderation analyses? Those interaction terms are almost always going to be small, right? So probably what you should do is if you really want to go through and power it and you do have the resources, I would just power it to detect a small effect, which is going to be in that type of analysis about 400 people, you know? And so, because otherwise, I expect to find a large interaction based on, because no one's ever done this before, and there's no research out there that even comes close to anything that I'm wanting to do. Like I'm having a hard time understanding why you would expect a large effect out of that. That seems like wishful thinking. Makes it comfortable thinking, but still wishful thinking. Okay. So Howell says, I don't know, often translates into, I haven't thought that far ahead. I think it often translates into, I didn't try, or I didn't think about it, or it was anxiety provoking for me to sort of think about that I might need 500 people in my study in order for it to be adequately powered, right? I'm not saying that all studies, and this is the thing sort of with milestones and theses and things like that, if you got a cool idea, I'm less concerned about if you're adequately powered to do it. If it's a cool idea, awesome. Graduate school is a time to do underpowered studies that are kind of innovative and kind of interesting. But what I would like you to know going into that is that, hey, I've got an underpowered study. I'm actually going to have to be looking for a relatively medium to large size effect in order for this to work. Could happen, but at least going into it, knowing kind of where you're at in terms of power stuff. Okay. Now, if you're writing grants, then we need to be more concerned with actually, do you have the power to achieve the objectives of the project that I'm giving money for? But sort of different approaches we can take to trying to guess where my power is, whether it's closer to 0.8 or 0.3 with stuff. Questions about this? All right, cool. So our non-centrality parameter, I've been teasing this for a while. If I calculate a test statistic, this is just my t distribution, this is one sample t, right? If I take my mean minus my reference value under the null divided by my standard error, that t statistic is distributed around 0, so long as sort of this thing that I'm subtracting is the true population mean, right? So I'm saying that this is a memory score for the population of adults. This is my estimate for supplement users. If supplement users actually have the same mean as the population, larger population of adults, then my t works out. This numerator is 0. The null hypothesis is true, and my distribution of scores actually follows the null distribution. Okay, but if the null hypothesis is false, and so that my mean that I'm testing is not equal to the population mean, then all of a sudden this equation isn't centered around 0 anymore, because this numerator is not 0, it's something else, right? And then what happens is we're not centered around 0 because we're subtracting the wrong population mean. But the population mean under the null isn't the population mean of my actual population. And so now we've got a discrepancy. And so what happens now is my t distribution is no longer centered at 0, it's centered around point sigma, okay? And sigma is our non-centrality parameter, okay? The shift from 0, from our central t distribution over to whatever that value is based on this, we refer to that shift or for whatever that is as our parameter non-centrality. What this does is, if we're looking at our power analyses, we're trying to see how likely it is that I find a value in this non-central t that exceeds my critical value of t here. Okay, so here is my null. Here's my null distribution. Here's my non-central t distribution. Because I actually do have an effect, power becomes an issue of sort of that non-central distribution. What proportion of that non-central distribution exceeds my critical t that I would expect under the null? Okay, and that shift, that non-centrality parameter, this is an indirect measure of effect size. How much different is my actual t distribution relative to that central t distribution centered around 0? People kind of get that. Again, this is why I think for the purposes of understanding some of these power calculations, this idea of overlapping distributions is maybe a little bit more, it translates better than sort of just doing something in the Monte Carlo replication an infinite number of times to see what proportion sort of falls out. Okay. All right, so down to brass tacks. What do we actually do with this stuff? Okay. What we're going to do is look at old school power calculations, is calculating our power, assuming specific values of sigma and alpha based on a sort of a tabled version. Now in your handouts in wild courses, you have a power table in there. You can go through and pull that up. But in simple cases, calculating power, not super precise, but it's easy enough, right? What I need to do to calculate my power is I need to get my effect size D in my single sample test. And then from that D, I just need to calculate my non-centrality parameter, okay? So here you can see non-centrality parameter is a function of your effect size and your sample size. Pretty straightforward, not anything too terribly complicated with this, okay? So in a hypothetical example, let's say we have, I hypotheses about people seeking treatment for psychological problems have higher IQs. People have heard this before, right? Like, oh, it's curse of madness. I'm sort of or the sort of curse of genius. I'm too smart for my own good. It means I sort of have psychological problems or something like that, right? So let's say what we did in this example, single sample test. We've got 105 individuals, or excuse me, 25 individuals, and we have a mean of 105 in our, I guess, people who are treatment seeking, right? And we know we have a population mean of 100 and standard deviation of 15 here. So what I'm first going to do is I'm going to calculate my effect size. This is easy, right? 115 minus 100 over 15 gives me my effect size. Okay. And what is that? Calculate that out. One third, right? 0.333. So what we then do, got our effect size. Go through and plug it in to get our non-centrality parameter. So we got 0.33 divided by the square root of 25, the people in our sample. Okay. Someone calculate that and tell me what that is. $1.65. Okay. So if I go up and look at my power table, okay, and I go through, and my value for my non-centrality parameter 1.65. If I go through on my sigma here and I drop down, I've got somewhere between 1.6, 1.7. I go over to alpha for my two-tailed test. What values do I have there for 1.6 and 1.7 on my table? What do you got, Basha? 0.36 and 0.40. That tells me the power of my test. So my test here, power, we'll call it 0.38. Someone will split the difference here, right? We'll say, assuming that the null hypothesis is false, my effect is expected to reach statistical significance about 38% of the time, given a sample of 25 and a population of effect of 0.33. Are we excited about that power estimate? Matt says no, why not?
Well, because the probability of making a type 2 error is much higher with the power itself.
Yeah, it's huge, right? If this is sort of what's going on, I'm probably going to have to wildly overestimate my effect. And then you sort of given this, about 2/3 of the time, I'm going to fail to reject the null hypothesis. That's not to say that the null is true, right? Again, if this is a true, if people seeking help for psychological difficulties actually are scoring 5 points higher than the general population in terms of their cognitive achievement performance, it's not nothing, right? It's not the same. It's consistent with my hypotheses, but with 25 people, I'm not going to have a very high-powered study. So these power calculations are pretty straightforward and not all that terribly complicated. But people sort of get how we got from 1 to 2 to 3 here. Okay. Other thing we can do is say, okay, well, I don't like power of 0.38. That's not helpful for me. What do I need to do if I get an adequately powered study? Well, this is easy too. We're just basically doing basic algebra here. If I know that my non-centrality parameter equals my effect size divided by the square root of my sample size, just rearrange that equation to get and solve for my sample size. So if I do that, I'll get n is equal to sigma over d squared. Okay. And so if I go through and plug that in, I get 2.80 over my sample or my effect size 0.33 and square that. Okay. Where did someone tell me where did I get 2.8? Yeah, Emily.
So do you go onto the appendix for power, go to the 0.05 and go down to 0.8?
Yep. Okay. So if we go down, we know at alpha 0.05, I want power to be 0.80. I just move across and I got my sigma value. Pretty straightforward, right? So someone tell me, take 2.8 divided by 0.33 and square that. What do we get?
71.99.
1.99.
71.
71.99. 71, so 72 people, right? So for this, if this estimate is effective, if I'm looking for an effect size that's 0.33, for a single sample test, I need 72 people in order to adequately power that, okay? So just some algebra, just moving back and forth, easy peasy. Questions about this? Yeah.
Do we only use LSD for this, or do we use any effect size?
Well, I mean, you can use any a measure of effect that you think is useful now. Generally, whatever you use is your, and this corresponds to calculating confidence intervals around effect sizes. Whatever you use as your standardizer should match the variability estimate that you're using for your test statistic. If you don't, sometimes it won't have a noticeable impact, but sometimes it will. So generally, single sample test is easy because there's only one variance estimate. As we start to move forward, you should probably use whatever variance estimate goes into the calculation of your standard error in order for everything to match up. Yeah, Emily.
So this calculation is for only single samples.
Yep, this is just for single sample. Okay. But your paired sample doesn't get too much more difficult. Again, looking for power to detect difference in our sample means. So once again, we just have our effect size, right? And then we're still looking for sigma. Sigma is just a little bit different for our paired sample test, or for our independent sample test. It's just d times the square root of n over 2, where n is the number of cases in either sample, right? This is my cell size here. Be careful because you'll get this turned around, not the full sample, just our individual samples. Okay. So let's say that I have looking for the difference in symptom means for treatment 1 and treatment 2. Okay. So I know that mean 1 minus mean 2, I get a 5-point difference with a standard deviation of 10 with 25 and 25 going on right here. So we're working in a situation where we have 0 violations of our underlying assumptions of our t-test. We have equal variances in each population, resulting in equal standard deviations. We also have equal sample sizes in this case. Okay. And so what we do then it's pretty easy. So if we calculate our effect size, 5 divided by 10 gives us 0.5, multiply 0.5 times the square root of 25 divided by 2. Someone tell me what we get there. $1.77. Okay. So if we go down on our power table, sigma is 1.77. We go down, we've got a value of 1.7, 1.8. And so we might say somewhere in between there. We're assuming power of about 0.43. Okay. Again, assuming the null hypothesis is false, effect is expected to reach statistical significance 43% of the time, given N25 per group of population effective t equals 0.5. And the same thing, if we want to take like, what's the sample per cell that we need to achieve power equals 0.8? Again, we just reconfigure our formula here, solve for n is equal to 2 times sigma over d squared, right? So we plug that in, n is equal to 2 times 2.80 over 0.5. Again, did my sigma change for power 0.5 for power 0.8? Nope, it's always going to be 2.8. That's just for a two-tailed test, the sigma value that corresponds to alpha 0.05. Someone tell me what this is here. Good, Elizabeth. Okay, here. Try. Okay, well, punch. I want everybody to be calculating this stuff. All right. Yeah.
I got 62.
62. What's that?
I got 62.72.
62.7. Okay, so we'll round up, right? So 60, 63. Right? So what I would need is 63 people per cell to go through, so I need 126 people in the full cell in order to adequately power this, because again, power of 0.43, I'm not super excited about that, right? Questions about what we did with our independent sample here? All right, but we rarely often have unequal, we rarely have equal sample sizes, right? And so what do we do if we don't have the same number of people in each cell? What happens, right? What we need in this case is to calculate a harmonic mean sample size for our unequal samples, okay? And so here our harmonic mean sample size is going to be 2 times the number of people in cell 1 times cell 2 over number of people in cell 1, cell 2. This is going to give us kind of a weighted mean sample here, okay? So going back through, if we take our stereotype threat example, okay? We have our control condition has our mean 9.64. We've got 18 people in that group. For a threat, 6.58, 12 people there. And then we've got a pooled standard deviation estimate of 3.1. Okay. So calculation of our sample size, pretty straightforward. We're going to call it D. We've called this G before, right? Sort of hedges G, sort of whatever. We get our effect size here. Go through and calculate that, gives us a value of 0.99 for our effect. So we've got a big effect going on here. So we've got a full standard deviation difference between these two groups, okay? But what I need to do now is remember that to solve for sigma, I need to have my effect size times the square root of n over 2, right? But because I've got different people, different numbers in each one of these, this is assuming that I'm going to run a study where I'm going to have an unbalanced design, right? So oftentimes, if we're looking at pre-existing groups, I might know that I'm going to have any psychological research. Let's say I'm looking at sort of differences, sex differences, right? I know in psychological research, I'm going to get a lot more women participating in stuff than men. And let's say I'm know upfront that I'm probably going to be able to like a 2-to-1 difference across men and women, right? And so it's not just that this study had a difference, I'm saying that sort of the balance that I'm going to get is probably going to be about the same. So what I need is I need to create or calculate this harmonic mean of my sample size. So what I'm doing here is I'm going to say if sort of this proportion is about what I'm intending to replicate, I take 2 times 18 times 12 all over 18 plus 12, right? Use that formula and I get a harmonic sample size of 14.4. Okay. And then I'm gonna take that, divide it by 2, right? And if I go through and take that, someone tell me what this is. 2.66. Okay, if I go 2.66, yeah. So somewhere between 0.74 and 0.77 on my table. So we say about 0.75. So this is actually getting close, right? So I say, assuming the null hypothesis is false, my effect is expected to reach statistical significance about 75% of the time, giving samples of 18 and 12 and a population effect of 0.99. Okay. Now, the thing to be aware of is, right, like notice what happens to my effective sample when I have an unbalanced design. Okay, so here I've got 30 people in my sample. Okay, 18 here, 12 here. When I calculate my harmonic n, what I end up is 14.4 people per group, right? If I multiply that 2, I end up with an effective sample that's less than the actual number of people that I collected. Based on this, what can we infer about the effect of unequal samples on my power? Emily? Okay, kind of, yeah, I think you're in the right vicinity. So what this is saying is, even though I have a sample of 30, effectively, I only have a sample of 28.8. So what does having an unbalanced design do to my power? Okay. It decreases it, right? And so recognizing that as my samples start to get out of proportion, effectively what I'm doing is I'm reducing I'm reducing the power of my tests. Not by maybe a whole lot. There start to become other problems, but if I've got a hugely unbalanced design, this starts to have impacts, practical impacts on my power, so on and so forth. Okay. So again, to the extent that we can have relatively similar cell sizes with these independent sample tests is awesome. Now, sometimes we can't, but we just want to, in the back of our mind, remember as we start to have sort of differences across there, we start to run into possibilities for like that starting to erode our confidence in our tests because we've kind of got violations. There's lots of stuff that can start to go wrong, particularly if our samplers are way out of whack. Sometimes we can't do anything about that, but it's something that we should keep in mind in the back of our heads. All right, last thing we'll go through our paired sample test. What's interesting with our paired sample test is for our power estimates for our paired sample test, we need to take into account the correlation between our time 1 and our time 2 estimates. Okay, this starts to become important and have a big impact on our ability to detect effects. So our effect size here is going to be equal to mean sort of time 1 minus time 2. So this is just our difference. And then here in our denominator, we're using the standard deviation of the difference scores. Very important that you're using the standard deviation of the different scores. Josiah, this is going back to what I was talking about there. One, and make sure, remember in our paired sample test, we've got sort of standard deviation of the control group. We can standardize using the square root of the average variances. These are nice because they put that metric more in line with what we would be doing for single sample and paired sample tests. It also improves interpretability, right? But remember that for our actual paired sample test, the variance estimate that we're using in the calculation of our standard error is the variance of the different scores, right? And so that's what we need to make sure that we're including in our effect here. And then what we've got is an adjusted variance here where we've got our, take what I just said, erase that, I got that turned around. That's for calculating confidence intervals around effect size, not for what we've got going on here, okay? What we've got going on here is a correction for our denominator here on our effect size based on the correlation between my 2 time points, okay? So what we've got here is a variance or a standard deviation estimate multiplied by 2 times 1 minus the correlation between time 1 and time 2, my 2 assessment points here, okay? So again, remember back on our t-test, I said, hey, you've got this D, which are repeated measures, which is our test statistic that we would calculate before, sort of our normal D calculated using average variances. We're going to divide that by 2 times 1 minus the correlation between my 2 time points. This is deriving from this power estimate that we go through and do here. Okay. So if we go through, and let's say, so we went through and used that Aronson model, right, and looked at that as an independent sample test, right? So we've got our threat group and our control group. And what was our power for that test or for that study? Yeah, it was like 0.4 something, right? Wasn't great. Yeah. But let's reimagine this study instead of as a between groups, as a within groups. Let's say instead of having threat group and non-threat group, threat group and control, let's say we bring the same 30 folks in, right? Because we had 30 people in the other one, 12 and 18. Let's bring them in and let's say we just take 30 people. So the same number of total people, we just first have them do a control set and then we implement a manipulation on the same people and then sort of have them do it under threat and sort of look at the difference there, okay? And let's say that the mean of the time 1, which is our control, and the threat, same as it was before. Is it the same as it was before? No, not quite the same. Less than it was before. Okay, before our threat had a lower score, but now here in the repeated measures, let's say we bump it up. Okay, so now it's 7 point. So there's even less of a difference than we saw in the between subjects thing. Pooled standard deviation across time 1 and time 2, or just the square root of our average variances, is 3.1. But let's say the test retest correlation between control and our second set is pretty high. It's 0.92. Okay. People seeing how we sort of changed this study around instead of making it into between subjects into a within. Okay. So if we do this and we calculate my denominator here, I've got 3.1, which is my pooled estimate of my variance across my 2 time points, times 2 times 1 minus my test retest, gives me a value of 1.24. Okay, so now if I take this divided by that, I get an effect size of 1.69. You can go through and do that to see that checks out. Okay. Now this is the problem with using sort of this type of estimate. I've got an effect size that's now quite a bit larger. It was big before, now it's really big. And this is hard to attach a practical interpretation to because it's not standard deviation units, it's corrected standard deviation units based on correlation. So it starts to get kind of tricky to try and say, oh, this is what this means. But if I use this measure of effect and calculate sigma now I've got my measure of effect size times square root of 30. Why did I just use, where did this formula come from? Yeah, perfect, Matt. And why does that make sense?
Use the same t-test to paired samples to the.
Yeah. Paired sample t-test is just a single sample t on your column of difference scores, right? So we're just using our single sample test here to calculate sigma. And if we do that, someone calculate this for me. What's 1.69 times the square root of 30? What is it? 9.26. If we look at our table, is that even on here? No. Okay. So we say, assuming the null is false, expected to reach statistical significance 99% of the time, given a sample size of 30, correlation between assessments 0.92 and a population effect of D equals 1.69. Okay. What happened to my power when what happened to my power estimate when I ran this as a between subjects versus a paired sample test? It went through the roof, right? Okay. So even though the difference in our two means was less in the paired sample, using the same number of people total, right? Even with less of a difference, it shot that up through the roof. We went from 0.3 to basically perfect power. It's functionally, there would be no way to not detect a difference, sort of given what we've calculated here. Yeah. You could say, I don't know, 30 is not, so you could say, you could talk about this as sort of being a very precise estimate, sort of given kind of what you've got going on. Now, would I use that as my metric of effect size to communicate? Probably not. For power, this is what we actually need to calculate power correctly. But in terms of communicating sort of what's going on to sort of an audience, this is probably inflated. This is where we worry about inflation of our effect sizes and sort of not having a real practical interpretation of what we've got going on here. So take home message, if I can sort of impart this on you all, our repeated measures designs are far, far, far more powerful, particularly with the types of samples that we have access to for theses, dissertation, experimental types of stuff, clinical work with difficult difficult to get populations, right? Again, and part of this is because for our repeated measures designs, one, we're only working with one source of error. Two, we've got this correction that accounts for the correlation between my two measures, okay? Our repeated measures designs, everybody counts as their own control, right? So all of that within between subjects variability, that goes out the window. Everybody could come in way different places. Everybody could leave at way different places. But if everybody's changing about the same amount, the variability of the column of different scores starts to go down quite a bit. and what we get is less noise. Okay, all the individual different stuff that people come in with, what mood they're in, how they typically respond to stuff, all that goes out the window when everybody's counting as their own controls. Okay, and then we've also got this correction to my effect is a function, or the correction to my standard deviation estimate is a function of the correlation between those two tests. As the correlation between my two tests or my two repeated assessments starts to get higher and higher and higher, that's driving that effect higher and higher and higher and giving me more and more power. Okay. So has anybody done psychophys types of stuff before? Sam, have you done psychophys work?
A little bit, but not really.
A little bit. Has anybody done psychophysiology stuff? A little bit.
I'm in Cynthia's lab, so
Okay. One of the things, if we're doing repeated measures with psychophys work, is if I come in at a certain level, like there's my biological system restricts sort of the amount to which I can change, right? So what we see with psychophysiology experiments is really, really strong correlations between, if I'm measuring at time one, sort of pre-stressor and post-stressor, something like that, those two measures are going to be really, really highly correlated. And what ends up happening is we have very, very powerful designs, because even with only a few people, the correlation between those two, one, you're already benefiting from everybody serving as their own controls, but then the correlation between those two measures starts to make these incredibly, incredibly powerful. Even small deviations across groups, you're able to pick up as an effect. Okay. Yeah.
Does sample size really matter with repeated measures?
Yeah.
Designs really, is there a number? Because like in general, it's like 30, but for repeated measures, is there a number that?
No, I mean, it just kind of depends. Well, it depends on one, how many people you got, and then the correlation. Now, as this correlation between my two assessments starts to decrease, then that starts to impact the power, right? To the point, if my effect size, if my correlation between my my two measurements is 0, essentially what I've got then is a independent sample test, right? Like your score at time 1 has nothing to do with your score at time 2. And so that eliminates a lot of the power within this test, because basically sort of time 1 and time 2 measurements are independent of one another. We could shuffle them all around. It doesn't even matter, right? If we weren't matching things up, right? But that's rarely the case. Now for psychophysiological stuff, that starts to become much more tightly correlated than if I ask you, say, your state mood across a week, right? Today, and I capture you next week sometime, your state mood, it's still going to be correlated, but not as strongly as that. And so then you're not going to get as powerful a test. It's still going to be powerful, more powerful than your independent sample test, but less so with self-report stuff that we will often do, right? So rarely do we have a correlation between time 1 and time 2 of 0. That would be a strange thing to find. Do people see kind of what's going on in terms of the power of these tests? All right. So again, if you can incorporate a repeated measure element into your design, it's worthwhile to do so. And then Katie, in terms of thinking about between subjects or sort of with sample sizes, as you start to get into more interesting types of repeated measures designs, we're often looking at mixed designs. We'll talk about those next semester, where I have both between and within components. Then you've still got a between component that starts to make sense to have more people. So they start to get a little bit more complex as we move forward with stuff. All right, calculations with G-Power. We've been doing a lot of this by hand, but G-Power is a nice tool for simple designs, for going through and estimating power with some stuff. Here is the link. Here's the basic setup for the little desktop app that you get. Here you can choose your family of tests. Here you can choose what type of test that you want to run within that family. Here you can choose what type of analyses that you want to run. Do you want to run a priori power, where you're looking at what samples do I need in order to achieve adequate power? You can do sensitivity analysis, say, these are the samples I have, what am I powered to detect? Sort of different options here. And then you've got different input parameters here. Choose a one-tailed or two-tailed test, your effect size, your alpha level, and sort of your power that you want. Okay, really easy, really straightforward. A nice, useful tool for identifying power for some more simple designs. Okay, so for example, if we want to run a single sample test, say we're interested in looking at the difference in extroversion scores in high school students relative to university undergraduates. We say previous research by Smith et al. Provides estimates of self-reported extroversion in the high school students in this measure of 65 and 13.5. Okay. Now, what we would do is we would choose our t-tests, and we would say difference from constant because we're doing a single sample test, right? Choose that. We want our a priori power. We want a two-tailed test, alpha 0.05 with power equals 0.8. Okay. Only thing we really need to do is plug in this effect size. Now, what we could do is we could take 70.1 minus 65.3 divided by 13.5, because we know how to do that, and just calculate our effect size and drop that in. Or you can just hit determine in G power, and what it'll do is it'll take you over this little screen. So here's your mean value under your null, your mean value for your alternative, standard deviation unit, then just calculate, and it'll calculate it for you. And then you hit calculate, transfer to main window, sticks it over there. So this is a nice way to go through and do things. You can calculate it by hand if you want. Or if you have an estimate of effect that you just know what the D is and don't know what that stuff is, then you just type it in there. So whatever you want. Okay. But if I go through and do that and then hit calculate, it's saying that what I need to detect in a single sample test with sample effect size 0.36, I'm going to need about 65 people in my sample in order to identify, be adequately powered. Okay, and then this is just your graph, that overlapping distributions. And that's what's going on here. Questions about kind of how we're setting this up? All right, same thing, independent sample T. Again, we've got just kind of a little description here about. So we've got data from a previous study. We want to look at this in a different population. So we've got some estimate of the type of effect that we're likely to find. In this situation, we're looking at marital satisfaction, right? So we've got 4 men and 21 women in this sample, which is sort of getting at some of that imbalance that we often see in psychological tests or in psychological research. So maybe we think, you know, this 4-to-1 or was it 5-to-1 ratio is probably about what we're going to get in our actual data collection. So then in G power, all we're going to do is we're going to identify difference between 2 independent means, a priori power, two-tailed test, alpha 0.05, power 0.80, allocation ratio. This is the imbalance, sort of like which sort of what to what. I guess I did instead of 5-to-1, I put 4-to-1, but 4-to-1 difference in terms of what I'm going to get across my 2 groups is what I expect. Again, if I hit determine my effect size, what I can do, a couple different options here. I can put in mean of group 1, mean of group 2, and then if I have equal variances is what I'm assuming, then I can just put in to whatever my standard deviation is and use that. Or I can hit this other thing, mean 1, mean 2, standard deviation 1, standard deviation 2. Calculate gives me my effect size, transfer that over. And if I go through and calculate that, now it's saying that what I need is 38 people in one group and 48 people in the other in order to get reach an effect size of 81. You'll see how we're just kind of sort of playing around with these fields and going through and getting things entered up. And then last, our single sample test, again, same deal, right? Here we've got kind of a scenario where we're wanting to know, we've got sort of a previous study that's doing something, we're wanting to look in a slightly different population. Again, we're just going to choose difference sort of between 2 dependent means, so it match pairs, still a priori power, two-tailed test, alpha 0.05, power 0.80, determine my effect size. And so again, here I've got mean of group 1, mean of group 2, standard deviation 1, standard deviation 2, correlation between my 2 groups, drop it in there, calculate and transfer over. No, I don't know why I didn't do that in the screenshot, but anyway, So it kicks it over and gives me an effect size of 0.7. And I go through and calculate, and it looks like for that 18 people in my sample, which is pretty slick. I'm happy about that, right? If I'm have a paired sample test, I need 20 people to adequately power my test. Awesome, that's super doable, right? Unless we've got some really rare population that I'm trying to track down with stuff. So G power is pretty easy, pretty straightforward. Calculating power by hand isn't all that terribly tricky. You're just kind of being precise because you're working with some tabled estimates. But for the types of means-based analyses that we are doing this semester, G power ends up being pretty slick for getting estimates. Questions about this? All right, so my write-up, pretty straightforward for power, right? We got an effect size of 0.45 expected to, based on existing data from Jones and colleagues, power analyses using these data indicated sample 32 individuals per group would be required to achieve adequate power. And I mean, so the big thing with our power analysis and write-up for stuff like that, what I want to see, or what I would want to see in like a publication or manuscript or something like that, is tell me exactly where you got that estimate of effect size, because that's really the crucial thing. Like, I'm expecting an effect size of this. Tell me why. Tell me what's led you to believe. How did you arrive at that estimate? Again, hopefully it's not hopes and wishes, because we always so may your effect sizes always be large. That's generally not the types of effects that we're chasing down in psychological science. But here we can say, hey, existing data from Jones and colleagues kind of did what we're looking for. This is our best estimate of effect based on what they found. Based on that, this is how many people we would need in order to achieve adequate power for this study. Pretty simple right up here. Questions? Okay. So finishing up, what happens if we did our due diligence? We went through, we estimated our effect sizes, we pulled it from the literature. Let's say we even followed Sam's example. We've got a meta-analysis that gave us a good estimate, aggregate estimate on our power. We go through, we power our study, and we still fail to reject the null. What happens? What do we make of this? How do we understand it? Right? Well, one, we have an error in our power calculations, right? I just made a mistake somewhere and screwed stuff up. That's a possibility. Two, my effect size is smaller than I estimated. Now, our meta-analysis is going to do a better because it's going to be an aggregate measure across studies. And if it's a good meta-analysis, they've gone through and pulled data from unpublished studies so that we don't have a file drawer bias with this stuff. But it's possible that we still maybe overestimate the effect that we're chasing down, right? So we were still underpowered. We did it right. We just overshot the effect that we were looking for. Or we're just a victim of type 2 error, right? We went through, we had our effect right. We had our power analysis right. We just ended up in that tail. Like, we didn't do anything wrong. We just got unlucky, right? I powered my test to be able to reject the null 80% of the time, but that still leaves 20% of the time where I'm going to make a type 2 error just because I don't got enough people. Okay. So, but based on, if I just turn up null, do I know which one of these things for sure I've done? I don't know. I don't know. I can go through and I can maybe make some guesses, and I'm going to want to go through and do a critical analysis of stuff. But what I wanted, but it's impossible for me to go through and say for sure. Quick finish up with observed power. Okay, this is a thing that comes up sometimes, and SPSS will give you estimates of observed power. Now, if I'm using power calculations appropriately, what I'm doing is I'm planning out for some future study. Okay, but what often happens is sometimes, let's say Katie runs a study, gets the study with the people she has, calculates her effect size, and then tries to figure out whether or not her study was adequately powered. Okay. And so the idea, this is observed power. Okay, given the effect size that I obtained in this sample, was my study adequately powered, right? And often the idea behind this is that, boy, if this was the effect size that I got, and I failed to reject the null with an adequately powered study, then maybe sort of this really is like I'm proving the null. There really is no difference. If I have an adequately powered study and I failed to reject the null, then maybe sort of what happens is that null is actually true. There really is no effect, okay? This is an enticing proposition. The problem is that our observed power that SPSS will give you, it's a direct function of your p-value, okay? So if you fail to reject the null hypotheses, you will always get an underpowered study. There's no circumstances under which you fail to reject the null and it tells you your power is good. By definition, if you fail to reject the null, you're going to have an underpowered study. Okay. So what people want to do is they want to say, boy, what I'm hoping is I'm going to calculate so my observed power. And if that comes back positive and I still fail to reject the null, that means there really is no difference. I'm kind of proving the null, right? Is that there's that even with a adequately powered study, I failed to reject, right? Problem is that can't ever happen. So that's never going to be the case, right? Alternatively, what people say is like, well, I went through and I failed to reject the null, right? But if I run my observed power, I'm seeing that my study was underpowered. Why is that a useless statement? Yeah, because we already know that. By definition, you didn't reject the null. So this is always going to tell you you're underpowered. So you're not giving me any new information, right? There's never a situation where you're going to be like, oh, well, I failed to reject the null, but like, no buts. We already know what happens with that observed power, right? And so this is this Honing and Heisey paper talking about power approach paradox. Make the argument that this observed power adds absolutely nothing, that it's basically a useless function. But wanting you to know all this because this is something that SPSS will provide and reviewers will sometimes ask for this. Be like, well, give me an estimate of your observed power because maybe you weren't adequately powered. Like, well, of course I wasn't adequately powered because I failed to reject the null. There's nothing new that's going on with this, okay? So, all right, we'll stop there, okay? Just to be clear, none of this stuff from today is going to be on the midterm. Like this is not, so this isn't stuff we'll worry about. You'll have problems of 5 that works on power and confidence intervals around effect size and things like that. We'll do that after the midterm, but don't worry about sort of any of this stuff for the task at hand next Wednesday. Okay. All right. So we'll leave it at there. Let me know if you have questions about any of the feedback that you got on problem set 3. CJ and I will go through and get problem set 4 scored back to you so you can look that over before the midterm. So I'll probably get those back to you maybe like Tuesday. That's not a lot of time, but there's not going to be much. Basically, everything I'm asking you to do in this set is just an extension of the stuff I asked you to do last time. So it won't take you too long to look that stuff over, but want to get that back to you so that you have some time to sort of make corrections. I might get it back to you. I might just be comments. It might not have sort of scores on them or anything like that. I just want to make sure that you get the feedback on that so that you can make any tweaks, adjustments before you come in to midterm on Wednesday. Okay. Awesome. Nice work, everybody. You're doing a great job. Keep doing what you're doing. If you have questions, let me know. Let CJ know. Otherwise, we'll see problem sets noon on Friday with sort of the outlines of what we want for that sort of moving forward. Awesome. All right. Thanks, everyone.